Thank you, Dr. Vozka, for that introduction. Hi, everyone. As he mentioned, my name is Genesis, and I'll be presenting on alkene quantitation and plastic waste-derived alternative fuels using GC GC-FID. So plastic waste has been accumulating at an alarming rate, especially with the increase in use of single-use plastics. And usually what comes to mind when you think of this plastic waste problem are probably sea turtles in the ocean with straws sticking out of their noses, or really giant floating plastic patches in the middle of the ocean, right? But the ocean only accounts for 3% of total plastic waste. The rest of it goes to landfills, where it can take years, decades for it to decompose. And then once it does begin to break down, it's contributing to this microplastic accumulation problem that we're also facing. If you can imagine, 79% of all plastic waste goes to landfills. And even in my really eco-conscious home state of California, we landfill 285 Olympic-sized swimming pools of plastic each day. More specifically, 63% of that total plastic waste is made up of polyolefins like polyethylene and polypropylene. And these polyolefins are what make up your shopping bags, clear food wrap, yogurt containers. So they're mass-produced, they're everywhere. But at the moment, there are less than half a dozen facilities in the United States that are actually capable of recycling polypropylene. An even lesser-known contributor are car tires. In 2021, there were 2.3 billion units sold in the world's tire market, and this amounted to 54.5 million tons of tires. But not all hope is lost. Through some common chemical conversion processes, we can actually take this plastic waste and convert it into something useful, like a potential alternative fuel. So we collaborate with two universities. The first university is the University of Chemistry and Technology, Prague in the Czech Republic. And what they do is they send us here at Cal State LA these alternative fuels that they made from scrap tires. So they take the scrap tires, break them down into tire chips, and then following pyrolysis and hydrotreating, we're left with these oils with characteristics very similar to that of fossil fuels. We also collaborate with Purdue University, and Purdue developed a novel low-pressure hydrothermal processing method that converts polyolefinic plastic waste into oils. And both of these processes produce oils that can be fractionally distilled the same way crude oil would be. Purdue used a high-temperature PAR batch reactor, which is pictured here, to convert the plastic waste into oils and then distill them into a gasoline fraction, diesel fraction, and a very small amount of heavy oil fraction. I'm not a chemical engineer, so I'm not going to be focusing too much on our collaborators' methods, but I always think it's important to know and to show how the samples we're analyzed are being produced. I also want to emphasize that regardless of the conversion process, both processes produce potential alternative fuels with a high concentration of olefins. And olefins, or alkenes, are unsaturated hydrocarbon compounds that contain at least one carbon-to-carbon double bond. So we have these potential alternative fuels, and you might be wondering, can I just put this in my car and save the world already? But that's not really the case. Using a fuel with a high concentration of olefins can be really detrimental to engine cleanliness, and it can cause these really ugly gum formations in the engine. Olefins are not necessarily all bad. They do contribute to the octane number and anti-knocking in engines, but this is a new problem we're facing because olefins are not normally found in these very high concentrations. And because of this, there are currently no methods for the detailed quantitation of olefins in these high concentrations. So we use LICO's Quadjet GC GC-FID with liquid nitrogen thermal modulator. And I know everyone here is an expert on this, but I was a student at this conference last year, and there's probably some students here that want to know a little bit more about the details. So the reason why we use GC-GC versus traditional one-dimensional gas chromatography is because fuel is a very, very complex mixture that can have thousands of different compounds. So we need that second dimension to be able to further separate it. 2D provides us with better separation, better peak capacity, and better sensitivity. We use a reverse phase column configuration, and we use flame ionization detector. This next slide just goes over a little bit more of the methodology that we used, but we use FID because we know it's one of the best detectors for hydrocarbons. And that's because based on previous research, we know that the peak area is equal to the concentration in weight percent. But as we also all know, FID is quantitative, not qualitative. So it tells us how much of something there is, but not what it is. And because of that, we have to build a classification map. So this is an example of a GC GC-FID classification. And let me just get my laser pointer here. So here at the top, we have our isoalkane region, then the N-alkanes underneath, followed by the monocyclo, dicyclo, and tricycloalkane regions, and the aromatic regions here at the bottom. So based on previous research, we know that isoalkanes and isoalkenes elute in the isoalkane region. Monocycloalkanes, olefins with one double bond, and linear olefins elute in the same region. Dicycloalkanes and olefins with two double bonds elute in the dicycloalkane region. And the same goes for tricycloalkanes and olefins with three double bonds. So this is really great information, but if we're trying to get a really detailed characterization of our fuels, it's kind of a mess. Everything's eluting with each other. And with FID, it kind of seems impossible to be able to distinguish between them using only FID. So because of that, we employed a derivatization reaction to relocate the olefins from their original positions. So to prepare a sample, I always like to include a little video because I'm a visual learner and sometimes I get lost with all the words. But this is just me preparing our sample. We use dimethyl disulfide, an internal standard, and iodine solution. We add that to our alternative fuel samples. We place it in the oven at 70 degrees for at least an hour, and then we treat it with sodium thiosulfate, and then finally our organic phase is analyzed. So the iodine and the DMDS initiate the reaction, and then the sodium thiosulfate stops the reaction. So when we employ this derivatization reaction, what's happening is that the dimethyl disulfide saturates the olefins double bonds and replaces it with two thiomethyl groups. And this makes the molecule heavier and more polar, and it elutes down and to the right on the chromatogram following derivatization. So now that we were able to relocate the olefins from their original positions, we can take the peak areas pre and post derivatization and calculate the weight percent of the olefins that were originally in our sample. We tested our method using what we refer to as a supermixture, which is basically every alkene we could possibly find on Sigma Aldrich and Fisher Scientific. It was about 23 alkene standards. So this is just a zoomed in screenshot of our supermixture before derivatization. And then after derivatization, we see that those peaks did disappear. We tested, we wanted to know a little bit more about the time conditions necessary for this reaction. So I worked with some undergraduate summer research students over the summer, and we tested different time conditions to see if, what is 1 hour really enough, or does it need more time? Is there something that we're missing? So we tested it at 2 hours, 3 hours, 4 hours, 5 hours, and then we tested it at 24 hours, and then even 36 hours, and it's 1 hour is more than enough, but nothing's going to happen if you decide to go on vacation or something over the weekend. Now that we have, our pre and post derivatization data, the calculation's pretty simple. We take the peak area pre-derivatization and subtract the peak area post-derivatization and normalization. But we can go as specific as down to whatever carbon number you want to take a look at. So for example, if we wanted to look at isoalkene C11, we would take the peak area pre-derivatization of C11, subtract peak area post-derivatization C11, and we are able to calculate that weight percent. This is just a screenshot of some results that we calculated from scrap tire pyrolysis oil. And as you can see, before applying our method, everything's bunched together. It's good information, but we want to get as much as we can out of our FID. So following application of our method, we were able to further separate these regions and get a more detailed characterization of what's in our sample and actually get the weight percent of olefins in those regions. So like I mentioned, we can go down to the carbon number. So if we wanted to take a look at C7 monocycloalkane from a gasoline pyrolysis sample, we see that the peak area pre-derivatization is provided to us from the FID. And then after normalization, we're able to get the peak area of olefins. And then finally, we know that actually 3.61 weight percent were olefins basically hiding in that region. We also validated our method and compared it to known ASTM methods. And we chose these 9 gasoline-like samples because we know that they go from high to low concentration of olefins. So we compared using iodine and bromine number methods to compare the trend of high to low olefins. So we know the bromine number can be used to estimate the percentage of olefins, and the iodine value measures the grams of iodine that are necessary to saturate these double bonds. Oops, my apologies. To saturate these double bonds in 100 grams of sample. Bromine is the same thing, that if you don't have 100 grams of sample, you can't really do this. But as you can see, our method does follow a similar trend. We're seeing similar results, and that's what we want to see. We also tested using the FIA method. And the FIA method, it does measure the total of olefins in a sample. And again, our method follows a similar trend as well, but the FIA method measures in volumetric percent while ours measures in weight percent. And compared to other methods, our method is much more detailed because it does go down to the carbon number. So I'm biased to say it's better, I don't know, but I would say it's definitely more detailed. So in conclusion, we introduced a possible method for olefin quantitation in complex alternative fuel samples made from conversion of plastic waste. We'll also be applying this method to diesel and kerosene samples. We are having a couple issues that I would love to get some feedback from all of the experts here in the room with me. So first, our diesel-like sample, it's a really heavy, complex mixture. When we have the diesel sample, we have a lot of isoalkenes. So when we employ the derivatization reaction, they aren't dropping all the way down to the aromatics region. Instead, they're actually dropping to the tricycloalkane region. So it starts to get a little bit tricky once we're doing our calculations, because that's an area of interest for us. So if you can see here, pre-derivatization and then post-derivatization, those peaks are appearing there. I've been discussing and we've been talking to organic chemistry faculty here on campus about possible alternatives to DMDS, heavier alternatives like, diphenyl disulfide and dibenzyl disulfide. That could possibly bring those olefins down and farther down onto the chromatogram into the aromatic region. So the calculations will come easily. But again, if anyone has any suggestions or any brainstorming, we'd love to hear it. One other kind of concern that we're having is that one of our standards doesn't seem to be derivatizing. It's the EZ cyclododazine standard. So right here, I don't know if everyone can see, it's kind of zoomed in now. I was actually able to use, it was my first time using our brand new GC GC-FID, so thank you, Lico. I was able to kind of play around with that and see, unfortunately, that it was not derivatizing. I also spoke to some organic chemistry faculty, and what they told me was basically because it's such a large molecule and in space, it could be twisted and there's different orientations, the steric hindrance might make it really difficult for the DMDS to reach that double bond. So again, we have a couple new students in the lab that have organic chemistry background, master students who are going to be kind of working on trying out these different alternatives to DMDS. But if anyone has any suggestions, any comments, we'd love to hear it as well. We'll also be submitting a manuscript soon to the Journal of Chromatography A, and some of you might be reviewers for that, so thank you so much in advance. And these are our references. And then finally, I just want to say thank you so much for the opportunity to be here presenting in front of you all. It's so incredible. Last year, attending this conference in Liège was one of the peaks of my master's program so far. And seeing all the names from all the papers that I've been writing is the craziest thing. Or all the papers that I've been reading is just the craziest thing. So thank you all again so much for your attention and your time, and I hope you enjoy the rest of the conference.